So a little background information from me as well, similar to what John showed. We have an estimate of pre-fishery abundance, and it has been declining. This figure showing the upper figure is the total pre-fishery abundance. That has declined by about 50% from more than 1 million fish returning to less than 500,000. And this figure also shows how this returning salmon is distributed among marine catch, which is still ongoing in Norway, river catch, and the spawning population. And the major changes is that the marine fishery has been largely reduced, and whereas the river fishery has more or less maintained, slightly reduced in later years. And actually, the result is that spawning populations has increased quite a bit from early 80s until the last few years. A large part of this reduction, I guess, is similar to we see in Scotland due to reduced marine survival. But there are also a very interesting difference in different regions of Norway. Where northern Norway since 1989 has basically had no change in the number of returning fish. Southern Norway actually had an increase due to liming after acidification of several populations has been reestablished, whereas Western Norway and Mid Norway has been declining and is still declining. These decline are linked to specific impacts from different anthropogenic pressures. A little bit about the Norwegian Scientific Advisory Committee. I've been heading that committee for now 12 years, and I guess we can regard this way of working as a success. We are now 13 researchers from 7 different institutions. They do not represent their institutions, so we are there as independent experts. And we have a group that consists of people with competence in all the major threats and all the major ecological knowledge and biological knowledge of Atlantic salmon. So that's the idea of this committee. A little bit before I go into the threats and impacts and pressures, a little bit about how we assess the status for each population. The committee does annual assessment of confidence limits attainment. We've done that since 2009. And here you see a recent map of attainment of spawning targets or conservation limits in the different rivers in Norway, about 200 rivers. And this assessment is based on catch statistics and combined with knowledge on exploitation. We do a lot of drift snorkeling, other console estimates, and for some rivers we have no local estimates of exploitation rates, and then we use mapping of the fishery and the efforts to set the exploitation level to be able to estimate the spawning population. And then we do Monte Carlo simulation to account for uncertainty both in the spawning target or conservation limits and the exploitation rate, and also the proportion of females in each size group. One interesting side effect of this management according to spawning target is really boosting data acquisition. I think a lot of river owners realized they couldn't be managing in the blind. So they started took initiative to start to get information, and particularly this drift snorkeling counting has increased a lot. And actually, of the 200 population we assess annually, 77% of these had different estimates of exploitation and spawning size in 2019. And interesting enough, this management according to conservation limits has been a huge success in terms of improving the spawning stock. This figure combines the total exploitation in Norway with open squares and the proportion of the stocks that attain their conservation limit. And you can see on the exploitation back in the 80s, we had more than 80% total exploitation. That's in sea and marine, in the marine and in the rivers. And it declined, and the dotted line is when we changed the management regime to management according to conservation limit. You see a sharp continuing decline in exploitation level and a clear increase in the proportion of stocks that attain their conservation limits. We are now approaching 90%. So basically, exploitation is more or less removed as an impact factor in Norway. I'd also like to mention the very important piece of legislation we have in Norway that helps us a lot. It's called the Quality Norm for wild Atlantic salmon. It's actually approved by the King in Royal Decree in 2013. It says that the salmon must attain their conservation limit, but also have a normal harvestable surplus, meaning that they should have a harvested surplus according to the survival conditions at sea. So, and they should not be genetically impacted by farmed salmon. That's the introgression challenge. And this legislation says that if a minimum of good quality is not obtained, relevant authorities should implement measures to restore the quality, and that's a kind of a relatively strong tool for management to work with. Just shortly, it has two axes, one related to the conservation limit attainment and the harvested surplus, and then this is combined by the genetic integrity of the population, which are currently measured as this P-wild based on introgression of farm Atlantic salmon. And it's a typical, similar to the Water Framework Directive system, one out, all out system. So the thing is that you have to be in this four green sectors to have sufficient good quality. We can do that for about 200 population. The remaining 250 population can also be classified. The status there based on a prediction model and spatial autocorrelation, and then benchmarked against local data and consultation through regional and local managers. So this is basically an overview of the stock status of all 448 stocks in Norway. Poor and very poor quality is about 40%, moderate 35%, and only about 20% of the stocks are in a sufficient good status to be to fulfill the requirements of this quality norm. The main reason for this poor status is significantly reduced surplus, harvestable surplus, and also genetic integration is very strong in a lot of rivers in Norway. And for all of these population, we do also do classification of impact factors. So this is simply a list of the impact factors we consider. It's a little bit different from what I saw in Scotland, but of course the impact factors are different, and we prioritize different in terms of what factors to consider. So basically, these are ranked from 0 to 3, from low impacts to high impacts, and most of this work is done based on available databases, and also a lot of work is done via GIS analysis on maps. Regretfully, we don't have the same strong local management bodies in Norway, so we can't ask, as you did, local management districts to provide this data. But of course, we have a hearing of the consultation of our results. So basically now for all 430 Atlantic salmon rivers, we have this table. Do not look at the details, but it gives you the quality in the center here, and the ranking and the classification of each of the impact factors for each river. And of course, these can be also presented as maps showing how they are distributed regionally. It's a really long table, 430 populations. If we sum up the anthropogenic factors and weigh them by their effects in each river, so this is a figure showing not only the number of populations affected, but also the effect size. And for the Norwegian salmon population, salmon lice infestation is by far the largest, the strongest anthropogenic factor, followed by escaped farmed salmon and hydropower, and a lot of the other ones. So this gives us a good data set to do the threat assessment. But this ranking of threats that we actually published some years ago started back in 2010 when we did the first work. We decided based on the job we were asked to do to try to develop a simple system in 2 dimensions in which we combine the effect of the different factors from a loss factor that reduces productivity or production in the river up to some factors affecting the population to the extent that they can actually threaten their long-term viability. So that is the effect axis, and we had a development axis, we called it, saying something whether this is a stabilized factor or is an expanding factor. And for these 2 axes, we have the number of affected stocks, geographical distribution, typical effect on production, number of critical endangered and or lost stocks, implemented mitigation measure along the effect axis. Each are then ranked in a large table from 1 to 4, and we have some other traits related to the development axis, the potential for effective measures, likelihood of further losses in production, and likelihood of more stocks becoming critically endangered or lost. When we started this process, I think the quantitative background for this was not that strong, so it was dominated by expert judgment. But as I've shown you, as we now have been through all of the different populations, we now have a much stronger confidence in our classification. The first time we published this kind of results where we see here, it was quite a lot of noise. People have some industries attacked us strongly and called it dart playing and other stuff. But nobody actually went into our big table and said that number was wrong. And today, I think this way of communicating the threats has been accepted by basically all authorities and all industries, as well as an important way of looking at the major threats in Norway. And currently, there is the high temperature has cooled down considerably. So this illustrates then this is from the latest assessment we did. We update this annually, and some of these threats have been moving around in this chart. And we see it's escaped farm salmon and salmon lice that are in the red area that are ongoing and expanding population threats. Whereas we have a group a little bit further down here, Gyrodactylus salaris, acidification, hydropower, and habitat alterations as stabilized population threats in this area here. So this has been quite successful and is, as I said, now a well-established foundation for the priorities that the management and our authorities are currently making when they try to handle the challenges that salmon are facing in Norway as they are facing in Scotland. Just like to mention at the very end here that we are now also working with sea trout. We've done a similar exercise for sea trout. We see the status of the sea trout populations. And here you see the major threats. And there's no surprise that sea lice is a major threat now in Norway. But also agriculture, road crossings, and hydropower regulation are important threats to sea trout. And we've done this based on 430 rivers, and we are currently in the process of doing remaining 825 rivers. Actually, I've been working on that today before this meeting, so there's a work in progress, and hopefully then once we have all the rivers mapped, then we can make a similar ranking of threats chart as we have for Atlantic salmon. That was what I had so far.